Hello everyone, let's get started. Today we will talk about shift register, SR latch, T flip-flop, and JK flip-flop. These are advanced circuit component built by latches, particularly D latch and D flip-flop. I would like to review the D latch and the D flip-flop first. So the first line here is the clock. We have 3 clock cycles. D is the input. And then we have a flip-flop and a latch. So if we have a latch, when the clock is low, then we have a hold function. The output will not change with the input, although the input changes here. It holds. But when the clock is high, the output change immediately with the output, with the input. So you can see input change like this. Output also change like this. So the function of a latch is very simple. If the clock is low, it holds to the, the last input. For example, the last input here is a high, then this latch is hold to the high signal when the clock is low. But when the clock is high, it changes immediately with the input. So you can see these are the changes. These are the changes. These are the changes, and these are the changes. They are the same. So we can say that the latch is sensitive to the level of the clock. When the clock is low, it's not sensitive to the input. But when the clock is high, it changes immediately with the input. And then we also have the flip-flop. Unlike the latch, the flip-flop is sensitive to the edge, rising edge or falling edge. In this particular case, it is sensitive to the rising edge. When the clock is low, or high, there's no changing, and the output of the flip-flop will not change either. So you can see, only when there is a rising edge, the flip-flop change to its input. You can see this is a high signal, and then it changes to a high signal until the next rising edge. This is a low signal. It changes to low signal. There is another rising edge, but the input is still low signal. Although the input change to high in the period cycle, but if at the rising edge, the input is low, then the output is still hold to low. So the flip-flop is only sensitive to the rising edge in this case. By multiple these elements, we can have a shift register. So we just connect the input of a storage element to the output of another output of the storage element. Then in this way, we can have a shift register. The clock signal are controlled by the same clock. You can see the same clock is connected to each storage element. And then we just need to connect all the storage elements sequentially. And these are the flip-flops. So they are sensitive to the rising edge. You can see that when we send in input data at this edge, it will trigger multiple shifts like this. So the input will pass through different storage elements like this. And of course, you can change your input to 0 and to 1 again. All the storage elements will have the same shape of waveform, but with different delays. You can see the QA has this input 1 cycle later. This is 1 cycle. QB 2 cycle later. QC 3 cycle later, and then 4 cycle later here for the QD. You can also connect the output of the last storage element back to the first, the input of the first element. Then you have a shift REN, a shift register. Or you can connect the bar of the complement of the output of the last element to the input of the first storage element like this. Then this is a so-called Johnson counter. So we can use this state diagram to explain the working mechanism of the Johnson counter. At the beginning, we have no input. And then we send one high signal to the first storage element. The first storage element has a 1, and then it do a shift. And then it do a shift until all the storage element has all 1s. Since we connect the complement of the output of the last storage element, this element will be passed to the first one as 0 because we have the complement. Then all the 0. So in the second half of the the state transition, we just send all 0s to the input, and then we have this output. So this one will be inverted to 1, and then send back to the input of the first element. So we have this case again. So we can divide the working cycle of the Johnson counter by all 1s and all 0s. Two parts. And then this, when we reach this state, we will follow this path. And then this is a cycle. This is a circle. So we can have some more advanced latches like this SR latches. So the SR latches can operate as a simple memory with two stable state at two outputs when S equals to R equals to 0. So you can see that this is S, this is R. We have two inputs and we have two outputs. One is a Q, the other one is a Q2. One is a Q1, the other one is a Q2. So the Q2 is a complement form of Q1. Then the output is a Q and Q bar. So if we send a 0 here and another 0 here, if S is a 0, R is a 0, then because these are two NOT gate and these are ones. Because this is a X and this is a NAND gate. So if S is a 0, R is a 0, this element actually holds. It will not change. This is stable state. If S is a 1, R is a 0, then it can set the Q, which means Q will be 1. And if we send a 1 to R and a 0 to S, then the structure is reset. The Q will be 0. We cannot make S and R simultaneously equals to 1 because that's not a stable state. This case will cause a race condition to happen when the input change to S and R are both 0. So when S is 0, R is 0, this is 1, this is 1, because these are two NOT gate. And this is a NAND gate. So we can see that, assume this is a 0. 0 and 1, which is a 0. And this NAND, we need to make the complement of this result. So this is 1. This is a stable state. If this is 1, then 1 and 1 is still a 1. And we have a NOT here, and then this is a 0. Again, if S is a 0, R is a 0, because these are two NOT gate, this is 1, and this is another 1. If Q bar is a 1, Q2 is a 1, 1 and 1, we have a 1 here, 1 and 1 is a 0. I'm sorry, 1 and 1 is a 1. And then we have a NOT gate here. And then this is the output here is a 0. Because this is 0 and then this part is also a 0. And we have a 1 here, 1 and 0, which is a 0. So we have a NOT gate and this is output is 1. So when the S and the R are both 0, this latch has a hold state. It will hold to the pure state, no matter Q1 is 1 or Q1 is a 0. they don't matter. If both S and R are zeros, then it has a hold. But if S and R is 1 and 0, so you have a set, the Q1 will be 1. If S and R are 0, 1, then you have a reset. The Q is a 0 and the Q bar is 1. So unlike the D latch or the simplest D latch, you can only have a hold and a load state. Here you have a hold, set, and a reset. You can control the value in the latch actually. You can also, add a another 2 NAND gate here. So in this way, you can have a control signal. Only when the C is high, your F and R can actually send into this SR latch. If C is a 0, no matter what the value of S and R, these two will always give you 1. Then that's a intermediate condition. The output of this structure will be wrong. So you can it's a meaningless value. So in this way, by adding a control signal, you can actually identify, you can avoid this risk condition. Because when the C is 1, then the output must be meaningful. So this is the truth table of the SR latch. And the left part is the truth table without the control signal. And the right part is the truth table has the control or enable signal. Here another truth table to summarize the relationship between the Q value in N cycle and Q value in the N plus cycle. So you can see this is hold. For these 2 rows, this is a hold. For these 2 rows, it's a reset. For these 2 rows, it's a set. And these are the condition, risk condition you need to avoid. By adding a extra component to the D flip-flop, we can change the D flip-flop to T flip-flop. This extra function, this extra component is actually a selector. It's a mux, 2-to-1 mux. You can select the input. You can select, the output from 2 input, Q and Q bar. And the select signal is of course the D, is the T. And then the output is a D here. You can connect a D to this D flip-flop. So this is the function of the T flip-flop. I will use a waveform to explain that. So you can see that this is also a flip-flop. So it's sensitive to the rising edge. Sorry. At the rising edge, if your T is a high, then the output will change, will be inverted. Originally, Q value is a 0, then if the Q is a high, it will invert it to 1. This is another rising edge. T is a 0. The output will not change. This is the third rising edge. T is 1, then it's inverted. Original value is 1, then inverted to 0. This is the last rising edge. T is also a 1. So originally it has a 0, then it will be inverted to 1. So the inversion operation is also called a toggle. So when the T is a 0 at the rising edge, the output of the next cycle will not change. It will has a hold operation. But when the T is 1, then you have a toggle operation, inversion operation. So if it's 0, it will change to 1. If it's 1, then it will change to 0. So we can rewrite the relationship between the Q value in n cycle and the Q value in n+1 cycle like this. By this Boolean algebra. And the last one is the JK flip-flop. JK flip-flop is a more complex than the T flip-flop. But they follow the same principle. Both of them are adding an extra component in front of the D flip-flop. So you can see that this is the Boolean algebra for this JK flip-flop. So in JK flip-flop, it's better than the JK latch. It has no race condition. So if J and K are both zeros, then you have a hold. If both of them are ones, then you have a toggle. If it's a 0, 1, then you have a reset operation. If it's a 1, 0, then you have a set operation. So basically, it has all the function we have in previous different flip-flops: toggle, hold, reset, set. So it's the most complex design. So this is the truth table to summarize the JK flip-flop function. And it has no race condition. It can perform all the operation of pure flip-flops. But it costs more hardware overhead because it the extra component has more gates. Any questions? So if no question, you can start to do your do the preparation on your presentation. The presentation will be due on next Wednesday. And then we will do the presentation in the class. So each one will rates the presentation from other groups. So the final project, and the 2 presentations are also graded by other students in the same class. Any question? So if no question, we can stop today. Thank you very much.